All right, guys, chapter 11. Now, a couple things about chapter 11. We are obviously not going to get through all of it. The first two sections, however, very important for you guys in the future on your SATs and when you take trig. The rest of the chapter is a review for you guys, so this kind of worked out nice for us. The remaining sections that we're not going to do are basically area of polygons, which you won't really see in the future, and then your volume and surface area that you guys touched on in middle school. So it's actually worked out okay for us. It's not ideal, of course, but 11.1 and 11.2 are, like I said, things you'll see on the SAT. So we're going to talk about some things in elementary trigonometry here as well today in this section. So let's get hopping, grasshoppers. 11.1, circumference and arc length. Now, you know what circumference is, so you're familiar with that. Arc length may be a little something new, and so we're going to put our ears on, focus on that point. First off, the circumference, of course, is the distance around a circle. You learned this back in the day. And let's see, this little paragraph right here kind of gives you a little history of it. Consider a regular polygon inscribed in a circle. As the number of sides increases, the polygon starts to get closer and closer to a circle, doesn't it? All right, it approximates the circle, and the ratio of the perimeter of the polygon to the diameter of the circle approaches pi. So therefore, that leads us to the formula that we get 2 pi r, or pi d. I always use 2 pi r, but obviously if you have d, then you can go straight to pi d. But it seems like in most cases r is given. So as I go through these examples, I'm a radius guy with these, but when obvious situations occur, you can go with pi d. All right, first example real quick. They give you the radius and they want to know the circumference. So the circumference formula, of course, I always like to start with the formula and just plug in what I know. So my circumference is 2 pi, 9 is the radius. So this is going to be 18 pi. And I want to talk to you guys about this for a second here too, because on your SATs, this could very well be the answer. All right. You don't always have to multiply this out. This book is talking about multiplying these things out to the nearest tenths or whatever. But on an SAT, I want you guys to get familiar with pi form or an exact answer. So if they say exact answer on an SAT, this is what they're talking about because you did not round it. So it's 18 pi is the length of the circumference. Now, for all intent and purposes, like if you're doing something out in your yard or you actually are trying to get materials or whatnot, you're going to want to take this out in your calculator. And most of the time, like I said in this book, that's what you'll be dealing with. So 56.5 centimeters is your rounded circumference, your approximate circumference. All right, in part B now, they give you the circumference, and you got to go backwards to find the radius. So again, I start out with my formula, plug in what I know. The circumference is 26, and I'm working it backwards to find the radius. So now be careful. If you're going to do this all at once, which is the fastest approach, in your calculator, make sure you use parentheses. That is a must, or else your calculator will divide by 2 first and then multiply everything by pi. And we don't want to do that. We want to divide by the quantity of 2 pi. Right? So my radius, and you can make sure you get the right answer. Make sure you're doing it right. Your radius is about 4.1. All right, so there's the first example. Again, trip down memory lane. Now, getting into the good stuff in this section, using the arc lengths to find measures. So now, pay attention here. We talked about the measure of an arc. That's different. That's different than the arc's length. The length is like, hey, I'm at A, and I want to travel to B. How far is that? It's a distance. The measure of the arc we did in chapter 10 was like the degrees of the arc. Well, the length of the arc is the actual feet or meters or whatever in linear units. So you got two ways that you can talk about arcs. The measure of an arc is in degrees, and the length of an arc is in feet or inches or meters or something like that. All right, so now the formula comes from right here. In a circle, the ratio of the length of a given arc to the circumference is equal to the ratio of the measure of the arc to 360. And it's all a lot of words here, but it should be pretty simple. But here's where the formula is derived. The length of the arc based on or compared to the entire circumference is equal to the measure of the arc compared to 360. Because the circumference is the whole way around, 360 is the whole way around. This is a fraction of the circumference. This is a fraction of the degrees of it. So now, for our intent and purposes here, what they do, they just multiply both sides by 2 pi r to get the arc length by itself. So this is the formula that's going to set you free. And again, you will need this on your SAT. And when you take trig, you'll have a refresher on this. This is early in the year, your junior year, so this won't be the last time you see it until you take the SAT. But and your trig teacher will go over this again with you. All right, but this is a geometry concept, so it's cool that we talk about it. All right, so great example here, example 2. You got 3 different ways that this could be asked to you, and we're going to talk about each way to tackle it. All right, the first one, let's see what we're given here in A. You've got the radius given and the central angle given. So let's follow our formula. The length of the arc, so I'm just going to call it AB without the little m next to it. The length of the arc equals the degree over 360 times the circumference, 2 pi 8 in this case is the radius. So logically, guys, what's happening is you're just taking from A to B. Well, that is just a fraction of the entire circumference. What fraction is it? 63/60ths. That's the fraction of the entire circumference. So that's the length of the arc. So now it's just a matter of putting all this into your calculator, because they don't want, like I said, sometimes it will be in terms of pi. So actually, let's practice that. 63/60ths you can reduce to 1/6, and then 2 times 8 is 16 pi. So an SAT answer could very well be 16 pi over 6, which reduces to 8 pi over 3. So now that could very well be an SAT answer. And for our intent and purposes here, though, in this book, it's going to accept the decimal answer, which in this case is 8.4. And again, this was in centimeters. So the length of the arc is an actual linear meters, whatever you want. All right? So now, B and C, same equation. They're just giving you different things. So let's start it out. Let's see here. In this case, we actually know the length of the arc, and we're trying to work it backwards to find the circumference. So same formula. In this case now, I've got, well, I'll just write the whole thing out for you. So I know xy has to equal 43/60ths times 2 pi r, or the circumference. Since they're talking about circumference, I'm going to go straight to just the big C instead of the 2 pi r. All right, now I know the left-hand side. I know that what xy is, so I'm going to plug it in. 4.19 equals 43/60ths times my circumference. So now if I can just multiply by the reciprocal of 43/60ths, which is 1/9, right? So I could really rewrite this as 1/9. So then I just have to multiply both sides by 9, and I got 37.7 as my circumference. So it's really just dealing with that equation. Arc length equals the central angle over 360 times the circumference. All right. And again, use your head. In this case, they gave me the radius in the first example, so I went with 2 pi r. And then the second one, they were talking about circumference, so I just went straight to big C and didn't worry about 2 pi r. All right, so over here, again, they give me the length of this arc, RS, and they want to find the measure of the arc. So they're going to be looking for that angle that goes on top of 360. So RS, the arc, equals the central angle, which I don't know this time, over 360 times 2 pi, and I know what the radius is. I'll plug it in next step. All right, so 44 will go here in place of RS. X is in that position now. And then R was 15.28. So 2 times pi times 15.28. All right, so now how do I isolate the variable when it's there? Well, the first thing you can do is multiply by 360 on both sides, and then divide everything by 2 pi 15.8. So when you do all of that, you get x to be 165 degrees. So again, just throwing it back to algebra here, get rid of the 360, and then divide everything by what your circumference is. And that'll get x by itself. All right. Now try the monitor progress, pause it, and let's see what you guys come up with. All right, so hopefully this is what we're looking at for these three. Followed right along with the last example. First one you were given. You might have messed this one up because 9, if it's written in the middle like that, then that's the diameter. So cut that in half to get what the radius is. I don't like how they do that, but like on the last one they pointed to it. If they draw a little arrow like that, it's pointing to just the one of the side, one of the parts. That's the radius. If they write 9 in the middle like that, right next to the center of the circle, that's implying it's the entire diameter. All right. Again, on an SAT, they'll say the diameter is 9 yards, just so you don't mess up. All right. 4, giving you the circumference, so just plug that in. Plug in your arc length and whatnot. And number 5, they're looking for the radius this time. And so now you just have to isolate R by multiplying by 360, then divide by 152 pi. All right, friends, moving along to some real life problems. Using circumference to find distance traveled. All right, the dimensions of a car tire are shown. To the nearest foot, how far does the tire travel when it makes 15 revolutions? So we want to get the circumference of this thing and then multiply it out and see what's happening. So circumference formula, of course, is 2 pi r. Now, from all of that, 15 plus 11 is 26 inches. So that's my diameter, so my radius is 13. And again, here's one of those situations where you can use pi d. So I'm looking at 26 pi for my circumference. So now it's going to make 15 revolutions. So you want to take that and you want to multiply it by 15. All right. That gives you 1225.2. But now the problem is this is in inches, and they want to know the nearest foot. So we got to divide that. So use your head all the time. That's an SAT trick also. Not really a trick, but just changing dimensions. They'll be simple like that. Feet, inches, things that you know. All right, so you can use the circumference formula to find distance. Distance traveled, things like that. It's good for like NASCAR. They're worrying about wear and tear on tires and things. Especially in the outer tire will actually have a bigger loop than an inner tire. They're always making lefts. So circumference comes into play with vehicles. All right, another good real world problem, example 4, using arc length to find distances. The curves at the end of the track shown are 180-degree arcs of the circles. So we've got like this situation happening right here. 180 arc, 180 arc. The radius of the arc for a runner on the red path is shown by 36.8. How far does this runner travel to go once around the track? All right, a lot of writing here, so I'm just going to uncover this bad boy for you. All right, so the path on the run on the red is made of 2 straight sections. So we've got our two straight sections here and here that are each 84.39 meters. And then we got to curve the track. So 2 times the length of each semicircle. And you might probably, maybe in your head, we're like, well, that's a semicircle, and that's a semicircle. So I can put them together and make one circle. And that is indeed true. They're showing you here, they're breaking it down as 2 times half of each circle. So 2 pi r, there's your circumference, and they did 2 halves. So you could cross those out right away and just go to 1 circumference. All right, so the runner on the red path travels about 400. And obviously the outer path is going to be different, right? We know that closer, that's why with sprinters, they angle or they shorten the lanes if the outer runners and things of that nature. It's all geometry, people. All right, try your monitor progress, pause it, see what you guys get. All right, so hopefully in this one, you were able to work it backwards. The car tire has a diameter of 28. How many revolutions does a tire make while traveling 500 feet? So I plugged in 28 pi to see what my circumference is. That was in inches. So 88 inches is 7.3 feet. So how many revolutions is 500 feet? Just divide it. You got about 68 revolutions the car would make. And the next one, this wants to know how far does the runner go around on the blue path? So the outer one. So everything is the same from the last one except for your radius changes to 44.02. So you can see the difference. The blue runner and the red runner actually run 400 versus 445. So whoop, there it is. All right, last concept today is a thing I was talking about with trig, radian measure for angles. So we talk about degrees in geometry and your whole lives to this point. It's been, this angle is 45 degrees or whatever. Well, there is another way to measure angles, and it is in radians. It's a little more precise, and it's something that is used a lot in trigonometry. You're just getting the foundation of it here. So I'm going to give you the background, the history of it, since you're an advanced math class. And again, your trig teacher will do this with you. But then the actual application of this is very, very easy. So don't get intimidated by all these words and what I'm about to say, because how we're going to use it is quite simple, actually. So let's just see where this is coming from. So measuring angles in radians. So what the heck is a radian? So let's see. Recall that in a circle, the ratio of the length of a given arc to the circumference is equal to the ratio of the measure of the arc to 360. So that was that arc length formula we talked about. All right, you had the piece of the arc divided by the whole entire circumference is equal to the degree of the arc over 360. A circle of radius 1 has a circumference of 2 pi, right? If you plugged in 1 for r is just 2 pi r, 2 pi 1 or just 2 pi. So the arc length of CD in this little picture, so the length of CD is the measure of the central angle here at CD over 360 times 2 pi, since r would just be 1. So it's just 2 pi r, 2 pi 1. Recall that all circles are similar. Yes, all circles are similar, and corresponding lengths of similar figures are proportional. So the fact that all circles are similar means this little circle and the bigger circle, they're going to be proportional. And that's true with any circles that you would compare, any two circles. So because, let's see, the measure of angle AB for that, the measure of that arc is the same for AB and CD. And AB and CD are corresponding arcs, you can write the following proportion. The arc, I'm right here now. So the arc length of AB, this length, is to CD's length as R is to 1. So proportional because they are similar. Arc length of AB, so then we're just taking this formula and manipulating it how we want. So multiply both sides by the arc length of CD, and now you have arc length of AB equals radius times measure of angle CD over 360 times 2 pi. Again, a lot of words. All that leads to more words. This form of the equation shows that the arc length associated with a central angle is proportional to the radius. And the constant of proportionality right there is defined to be the radian measure of the central angle associated with an arc. So in a circle of radius 1, the radian, and you're going to talk a lot about this in trig, that's a unit circle. The radian measure of a given central angle can be thought of as the length of the arc associated with the angle. Right? A lot of words, very simple, the application of it. I just wanted to give you a brief history of where this stuff is coming from. All right? And all it's going to be for us is converting between degrees and radians. There's two ways, two things. If you have degrees to radians, you're just going to take pi over 180. And if you're going radians to degrees, it's 180 over pi. Watch how cool this works. So 45 degrees. How many what radian measure is that? Well, quite simply, guys, since I have degrees, this is how I always remembered it. If you have degrees, you want the 180 on the bottom so that the degrees will cross out. So then you just have to simplify 45 over 180, which is 1/4. So the pi just chills here still, and you have pi over 4. So 45 degrees, oh my gosh, and when you guys take pre-calc, you're going to use this one a lot. 45 degrees is pi over 4. Same type of way to angle measure. So now in the part B though, now they give you the radians. So you'd want the radians on the bottom so that they cross out. So 3 pi over 2, and the word radians might be messing with you here a little bit. So let me show you how I kind of deal with this. If I see 3 pi over 2 radians, I'm like, all right, well, 3 pi over 2, and then you're multiplying. Those of you who took chemistry, it's kind of the same way when you get rid of your units and convert units and things like that. So like, I know I need the radians, the pi on the bottom, so I put the 180 on top. So it's either going to be pi over 180 or 180 over pi based on what you have. First one we had degrees, so I put the 180 on the bottom. And the word radians, like I said, you're not really even gonna take a look at that when you're doing this quickly. So now I'm like, all right, the pi's cross out. I can reduce 2 in 180. So 3 times 90, 270 degrees. And you'll memorize a lot of these after you take pre-calc. But I don't know. I kind of like the way I do it a little bit better, just because the word radians might mess you up. All right, pause it, take a look at this last one, see what you guys come up with. All right, and finally, we've got pi over 12, and then let me work this last one for you. You've got 4 pi over 3. So again, I want to have pi on the bottom of the second term so that they cross out. And 3 and 180 I can reduce to 60. 4 times 60, 240 degrees. So a 240-degree angle in a world of radians is 4 pi over 3. A 15-degree angle in the world of radians is pi over 12. All right, guys, I know it's a long one, but we're wrapping things up here. Peace.